In this video, we're going to talk about feature engineering, scaling, and feature selection. This is a step that we normally would conduct after cleaning the data for machine learning. Let's start by defining features. A feature is an individual measurable attribute describing the data, depicted as a column in a table in this example. Each column is a feature, except for the last column, which is the called label and is what we want to predict in the case of supervised learning. In this table, each observation is a row, and each feature will have a specific value for the observation. Each row typically indicates a feature vector, and the entire set of features across all the observations is called a feature set. Features are of two types. There are inherent raw features. These features are those obtained directly from the data set without data manipulation or engineering, whereas derived features usually are obtained from feature engineering from existing data attributes. In this lecture, we will focus on the feature engineering. After the data has been processed, there are three steps, namely feature engineering, scaling, and feature selection, which may be needed to get the final set of features that will be used in machine learning modeling. Why do we need feature engineering? Well, raw data cannot often be used to build machine learning models directly. Feature engineering is essential for model building and evaluation. It provides a better representation of data such that the data can be better understood by the algorithms. In general, if you have the right feature set, even a simple model will perform well. Feature engineering helps us build models on diverse data types, therefore it enables us to work on complex unstructured data. Feature engineer also enables data scientists to take a step back and try to understand the domain and the business problem better by taking inputs from domain experts. Depending on the model to be used, data may need to undergo some transformation. The chart below shows the different transformations that can be applied to the variables depending on the type of variable, numerical or categorical. We will review some of these in the next slides. Let's talk about feature engineering on numerical data. The numerical raw data can be a value or a count, let's say like a frequency of some attribute. Described in this slide are some feature engineering methods for numerical data. There are cases where the raw frequencies or counts may not be relevant for building a model based on the problem which is trying to be solved, and maybe only the presence or absence of the feature is relevant. In those cases, binarization could be applied. In other cases, when dealing with continuous numeric attributes like proportions or percentages, we may not need the raw values having a high amount of precision. Thus, it often makes sense to round off these high precision percentages into numeric integers. In these cases, we would apply rounding. We can also bring together features that we know have some type of interactions, and in this case, use that as part of the input feature set. This is called, we would use then interaction. In other cases, we may need continuous numerical features to be discrete, and in this case we could apply binning. Finally, some machine learning algorithms work well when the data follows a particular distribution. Thus, we may need to perform some transformation to the data to follow the same distribution, or to adjust to that distribution. And these will be statistical or mathematical transformation methods. I am only going to describe in more details a couple of these methods. Binning is the process of grouping raw values into discrete numbers or bins. There are two types, fixed width binning and adaptive binning. In the fixed width binning, as the name suggests, we have a specific fixed width for each of the bins or buckets, which are usually predefined by the user analyzing the data. We're not guaranteed that all bins will be similarly populated. Some of the bins may be densely populated and some others might be sparsely populated. If your data is evenly distributed, fixed width binning might work well. In the graph depicted on the bottom left, for car prices and number of cars sold for that price, it is evident that the distribution of data values is skewed towards the cheapest cars. In this graph, the bins are indicated by the red lines, and we can see that they are all the same width. To solve the issue of this uneven distribution, the adaptive binning is a safer option. The data distribution itself informs the binning, in this case the quartile. Now we can see there are approximately, in this case, the same number of cars in each of the bins, again depicted by the vertical red line. In terms of statistical or mathematical transformation, these are used for skewed data distribution, making the distribution as normal shaped as possible. We have an example here for log transformation to make the distribution more normal-like, and the same with box-cost transformation. The log transformation reads log of x to the base b is equal to y. The box-cost transformation formula we have here has a prerequisite that the numeric values to be transformed must be positive. So let's check now how to deal with categorical data. Categorical features are often strings that need to be represented in numerical format. Hence, usually you might need to transform these features into a more representative numeric form. Even ordinal features might be presented in text format, and you need to map the transform them into numeric representations. Encoding is the process of converting categorical or textual data into numeric format. In this slide, 3 encoding methods are shown with an example. For nominal data, one hot and dummy encoding can be applied. This is on the left on the slide. One hot encoding, the top one. In this method, each category, in this case will be the color, for the feature color, is represented by a unique binary vector of zeros and 1. For example, green will be 1, 0, 0, 0, red will be 0, 1, 0, 0, and so on. Each of these vectors is unique. In the case of dummy encoding, after you perform this operation, you will drop one of the categories, and that category will assume to be all zeros. The example on the right is for ordinal data. In this case, we want to map the increasing size. We have different sizes, extra small, small, medium, large, and extra large, and we want to map these to numbers. And these numbers has also to be, in this case, increasing. The label encoder class from scikit-learn can be used to generate this mapping scheme. You can also apply other encodings. One is called bin counting. This is useful for dealing with categorical variables with many categories. It converts the variable into statistics about the value. Or you can do feature hashing, which is another useful feature engineering scheme for dealing with large-scale categorical features. A hash function is typically used such that the hash values of the features are used as indices in the predefined feature vector, and values are updated accordingly. In addition to the data types we saw, we can do feature engineering on temporal data. Temporal data contains features that are date-based and time-based. Or text and images. These are other data types. There are specific strategies to deal with all these different data types, but these are out of scope for this lecture. Another transformation we may need to do is feature scaling, as using the raw values as input features might make models biased toward features having really high magnitude of values. The next slide will describe this. When dealing with numeric features, we have specific attributes which may be completely unbounded in nature, like for example, web page hits. Using the raw values as input features might make models biased toward features having really high magnitude of values. This is because machine learning model just sees numbers, and if there is a vast difference in the range of value, it makes the underlying assumption that higher ranging numbers have superiority of some sort. Models such as linear or logistic regression are typically sensitive to the magnitude or scale of features. On the other hand, tree-based methods can still work without feature scaling. Feature scaling offers the techniques to standardize the independent features present in the data into a fixed range. Standardized scaling tries to standardize each value in a feature column by making the mean 0 and scaling the variance to be 1 from the values. This is also known as centering and can be denoted mathematically in the formula depicted here, where each value in feature x is subtracted by the mean mu of x, and the resultant is divided by the standard deviation of x. You can also divide the resultant by the variance of the standard deviation if needed. Another scaling technique is called min-max scaling, that scales all the data between 0 and 1. And here is the formula. The scale, in this case, each value in the feature x by subtracting it from the minimum value in the feature min x and dividing the resultant by the difference between the maximum and the minimum for x. Even though the scale is 0 to 1 in this scaling, the min-max scaler class in scikit-learn that you may use in your tutorial also allows you to specify your own upper and lower boundary in the scale value using the feature range. The last scaling method we will review is called robust scaling. The disadvantage of min-max scaling is that often the presence of outliers affect the scale values for any feature. Robust scaling tries to use specific statistical measures to scale features without being affected by outliers. Mathematically, this scaler can be represented by this formula, where the scale each value of feature x by subtracting the median of x and dividing the resultant by the interquartile range of x or IQR, which is the range difference between the first and the third quartile. Dealing with a large number of features brings us to the issue of the curse of dimensionality, which means more features tends to make models more complex and difficult to interpret. Also, irrelevant and redundant input variables can distract or mislead the learning algorithms, possibly resulting in low predictive performance. Besides this, it can often lead to models overfitting on the training data. Feature selection is a group of techniques for selecting an optimal number of features to train and build models that generalize very well on the data and prevent overfitting. The techniques are grouped into those that can be applied to supervised and those that can be applied to unsupervised learning. In the former case, there is further classification based on the models that automatically select features as part of fitting the model. Thus, these are called intrinsic models. Those that explicitly choose features that result in the best performing model, these are called wrapper methods. And then those that score each input feature and allows a subset of the selected features. These are called filter methods. Here's the definition for each. In the case of the intrinsic methods, It used machine learning models to rank and score features variables based on their importance. Tree-based methods like decision trees and ensemble methods like random forests are popular examples of these intrinsic, also known as embedded methods. In terms of wrapper methods, these techniques try to capture interaction between multiple features by using recursive approach to build multiple models using feature subsets and select the best subset of features given the best performing models. In this case, backward selecting and forward elimination are popular wrapper-based methods. Finally, filter methods. These techniques select features purely based on metrics like correlation or mutual information. These methods do not depend on results obtained from any model and usually check the relationship of each feature with the response variable to be predicted. Popular methods are threshold-based methods and statistical tests. Here are the references, and I hope you learn something new. Thank you.